Okay, so we're going to use conservation of energy to take a look at something that is talked about a lot in basically space. It's something called escape velocity. And that is the velocity to shoot off into space and never come back. So we're going to take a look into the escape velocity for Earth. Basically that means if I can find out how fast I need to make something go, then if I throw it, ignoring air resistance as it leaves the atmosphere, but if I could throw it that fast, I would throw it enough where it escapes from the Earth's gravity and never falls back down. So if I've got something going fast enough, it never comes back down. Okay, it's not quite like a rocket engine, because a rocket engine is not just a projectile motion where it's being thrown and you have to give it some initial energy that it's working off of. A rocket doesn't go nearly this fast because it supplies a constant force over a given period to actually get the rocket up into space. And for that matter, those rarely actually make it to what would be considered escape velocity. Well, they don't get up to the escape velocities, but they're never in a position where they would shoot off into space and never fall back down. We've only had a few things that we've set up that successfully do that, some of which are the Voyager spacecraft. But how we're going to do this, we're going to take a situation where we're looking at the Earth. It's not two Earths. We're going to have an initial energy and a final energy. We're going to have so that's our Earth. There. Not the best drawing ever, but it'll do. We've got a situation where we've got an object here on Earth, and we'll have it just on the surface of the Earth, starting off. And then at the second location, we're going to say that it's some distance really, really far away. In fact, we're going to look at the distance between it and technically the center of the Earth is going to be infinity. In fact, I should be drawing that a little bit better. Because if we've got a situation where the thing leaves Earth and never comes back, that means basically it's just going to fly off into infinity. It may take an incredibly long time for it to get there, but it's going to fly off into infinity. Again, one of the limitations with energy is it only tells you what's going on, it doesn't tell you how fast it happens. Okay? So escape velocity is based off of the idea of an object getting infinitely far away from Earth. If we've got a situation where it's going fast enough to escape Earth's gravity completely, then it'll just keep flying off into space and never come back. Our distance will become infinity. So, in this case, I start off with my object being a distance of the radius of the Earth away from the center of the Earth. I've got two types of energy that we're dealing with here. We're going to ignore anything like atmospheric drag or anything like that. We're just going to look at if I were to throw something at this given speed, I could throw it up into space and it'd never come back without paying attention to things like drag or anything like that. Although the atmosphere would be pretty thin to it compared to the velocities we're going to see. We've got two types of energy. We've got a situation where we've got potential energy due to gravity, and we've got some kinetic energy. And these are going to be at our initial position. And then finally, we're going to have a situation where we've got some potential energy due to gravity at the end, plus some kinetic energy at the end. Okay? So, in this case, we can't use simply potential energy due to gravity is mgy, because we're not near the surface of the Earth. So just like before when we couldn't use the force of gravity equals just mg, now we can't use mgy is our potential energy due to gravity. But we do have another equation for it. We know that the potential energy due to gravity in general equals negative g mass of the object divided by r. Sorry, potential energy is then the mass of the object too. So it looks very similar to what we saw with Newton's law of gravity, but in this case, instead of the r squared, we just have one value of r itself. All right, so let's take a look at our initial energy. Our initial energy, we've got a situation where it is our potential energy due to gravity. Well, that's going to be negative g mass of the Earth, because that's the object we're dealing with, mass of whatever object we've got that's going to go away from the Earth. So that's got some mass m, over radius of the Earth, because our distance between our object and the center of gravity there is going to be the radius of the Earth. All right? So this is our initial potential energy. Our initial kinetic energy plus 1/2 mv0 squared. And we want to find this v0. Okay? All of this together is my initial energy. Well, I don't know my velocity here, and I don't know my initial energy. So even though I know this, I don't know my mass, so that could be problematic. There's a lot of stuff I don't know. That's not good. All right, let's take a look at our second location for our energy, E1. That's going to be equal to our potential energy due to gravity at point 1 plus 1/2 mv1 squared. Okay, well, when I plug in my other equation here, negative g mass of the Earth, mass of my object divided by r, plus 1/2 mv1 squared. Now this is where some of our definitions actually come in. We're going to have to apply some knowledge about how we've defined escape velocity. Normally how we do it is we say that escape velocity is the velocity that lets you barely get off to infinity. So basically that means that v1 is free to equal 0 meters per second. Because if you're at 0 meters per second, then you just got there to infinity, as difficult as that is to imagine. If you're going faster than that, then great, you're going to keep going off to infinity. Again, difficult to imagine. But for escape velocity, we say that our final velocity, it basically barely makes it to infinity and is just kind of sitting there at that point. So this is going to go to 0. Now we'll take a look at this other guy here. So we know this, don't know that. But what about our radius? Our radius here, well, we said it's infinite. If we plug infinity, something divided by infinity, normally we take the limit as this goes to infinity, and we'll find that this effectively goes to 0 as well. Uh-oh. We just found that our final energy equals 0 joules from our potential due to gravity, plus 0 joules for our kinetic energy. Well, potential energy is relative. We can kind of define a lot of different places to be 0, although with this universal gravitational approach, we define our potential energy to be equal to 0 at some r equals infinity, infinitely far away. Basically, the thing that we take from this is our final energy, for one reason or another, comes up to 0 joules. We have 0 total energy in this system at the end. Okay? Well, let's go with that. Let's say that our total energy is equal to 0. That gives us a value. Let's go back to what we saw earlier. Our initial energy equals, where did we put that? Here it is. Yeah. Negative g times mass of the Earth divided by radius of the Earth, I guess I should make that a capital R, times our mass here, plus 1/2 mv naught squared. That's our initial energy. And by conservation of energy, our initial energy should be equal to our final energy, which means this whole thing should be equal to 0 joules. Actually, we should be able to do that. This guy's positive. This one's actually going to be negative from the way we deal with potential energy. It's a negative sign there. And so when I start plugging this in, I'll have that, let's see, I can add this over to the other side. Capital. So now I'm at a situation where I've got 1/2 m v naught squared, my initial energy, equals g times mass of the Earth times mass of my object divided by the radius of the Earth. Well, I didn't know what my mass was, but conveniently it cancels out. I can multiply both sides by 2. I find that my initial velocity, my escape velocity, because that's how fast I need it to go off to infinity, equals g for the Earth, mass of the Earth, divided by radius of the Earth, times 2. I'm going to take the square root of both sides. My escape velocity, which is my initial velocity here, equals the square root of 2g mass of the Earth divided by radius of the Earth. If we plug in where g is equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, our universal gravitational constant, mass of the Earth equals 5.94 times 10 to the 24th kilograms. And finally, radius of the Earth equals 6.38 times 10 to the 6th meters. I plug in those values, and I don't forget that little 2 there, and I come up with my initial velocity, which is my escape velocity, how fast something needs to be going if I were to throw a ball, ignoring air resistance in the atmosphere, for it to go off into space and never come back. It goes up to right at about 11 kilometers per second, 11,000 meters. I think it comes up to 11,100 meters, but it's usually quoted as 11 kilometers per second. Something's got to be moving pretty quickly for it to be thrown off the face of the Earth and never come back down. But this is the escape velocity for Earth. You can go ahead and take a look, and this is actually what they'll quote. You can go through, and this is more or less a general equation. We can find our escape velocity, and it'll be equal to the square root of 2 times gravitational constant times the mass of whatever object you're trying to get away from, so Mars or the moon, and then the radius that you're at, normally the surface, the radius of the object itself, and so the surface escape velocity. And so but we can see that that comes from using conservation of energy. And strangely enough, the way that we've defined potential energy, gravitational potential energy, we end up with 0 total energy in the system, because our gravitational potential energy is actually a negative. So, this is escape velocity.